All right, let's go ahead and get started. I've graded about half of the exams, and the other exams I only have one problem left to go. So I'll finish those today, put the grades in the grade book, and if you're really anxious to get a hold of your test paper, feel free to stop by my office. Otherwise, we'll go over the solution together on the Tuesday after Thanksgiving. I mean, I was hoping everyone would get 50 out of 50, and that didn't happen. But maybe, I think they're probably better than the first exam. All right, so you only have one more homework assignment, and it's due on the last day of the semester. Ordinarily, our assignments are due before class on a class day. But this homework 11 is due the day after class simply because that will give us a chance to spend a little bit of time on Thursday the 2nd talking about grade lines. And there's a small grade line problem on that homework 11. So we're moving on to chapter 7 in the book. Any questions before we start talking about the energy equation? Okay, we had a preview of the energy equation when we were talking in lab this past Tuesday. The background, remember that so far we've been looking at a variety of equations that allow us to predict the pressure in a fluid. We started with the hydrostatic equation, which described the pressure as a function of depth in a fluid. And we talked about the Euler's equation and Bernoulli's equation and the equation for irrotational flow. Those were all applications that take into account some acceleration and describe the pressure at a depth or the pressure at a certain location. And of course, it's not just pressure. There are other terms in each of those equations as well, like velocity terms, elevation terms. But the key thing that we usually want to know, at least in terms of civil engineering, is at a certain location, what's the fluid's pressure? And so we've considered a variety of forces that are acting on a fluid, like shear stress. We talked about in chapter 2 of the book the effect of shear stress on the shear stress that is applied in a fluid and the resistance due to the viscosity. But we haven't yet addressed some way to account for pipe friction or the energy that's required to move a fluid from one location to the other. So with the energy equation, we can also move into the description of power. And the hydropower equation we'll look at not next week, the week after next, and find out the watts required to move a fluid with a pump or the amount of watts that can be generated if we're using a turbine and having it in a hydropower type situation. The effect of pipe friction can finally be addressed, and we can move away from some of the pesky assumptions that weren't very realistic with Bernoulli's equation, and we can use the energy equation to calculate what's the flow rate when water's moving through a pipe and is being driven by some pressure differential. Local losses is what we talked about in the lab on Tuesday, and those bends in the pipe and fittings and other types of obstacles that the flow may encounter on its journey between origin and destination. So the effects of those obstacles is typically to reduce the flow rate, and we can quantify how much the flow rate is reduced by those obstacles. So here's the Bernoulli's equation. Remember that it was a relationship between the elevation, pressure, and velocity head under a few key conditions: that we have steady uniform flow, I guess we should say steady flow, uniform flow. It's applied along a streamline, and it's for an inviscid fluid that is incompressible. So there were quite a lot of assumptions that go along with the Bernoulli equation. The energy equation looks similar in that it has several of the same terms, although with some minor variations. So if you compare the Bernoulli equation to the energy equation, you can see that there's still a pressure head term. So P1 divided by gamma. Here in the velocity head term, though, we're not referring to the velocity at a specific point like we were with the Bernoulli equation. The Bernoulli equation, remember, was along a streamline. So location 1 was actually just a single spot in space. Whereas in the energy equation, location 1 doesn't necessarily refer to a streamline. Let me show you what I mean by that. So in the Bernoulli's equation, here is a nozzle, and let me draw the streamlines that just kind of indicate the relative direction of the flow paths. So when we were applying the Bernoulli's equation, we would say here is location 1 and here is location 2. So it's like a specific spot in the flow field. But with the energy equation, what we're saying is it's at an entire cross section. Like here is location 1 and here is location 2. So it's across the entire width of the pipe section. It's not at a single spot, but it's for the entire cross section. And so that's why we use here the average velocity. So V with the bar over the top of it means the average velocity that occurs at the entire cross section, not the specific velocity at a single point. So because of that, we add a kinetic energy correction factor. That's what alpha is. I'll tell you in a moment what that kinetic energy correction factor, why it's there. But it's in part related to the fact that we're using the average velocity instead of the velocity at a single point. There's also an elevation term, so that's the same between Bernoulli's and energy equation. But you'll notice that now there's a couple of other terms as well. H sub P, H sub T, H sub L. So we'll talk about each of these on the next slide. There's one other thing I wanted to tell you about the difference between Bernoulli's and energy equation, and that is that Bernoulli equation, it doesn't matter where is location 1 or location 2, because the same terms are on the left-hand side as are on the right-hand side. So with the Bernoulli equation, you're not going to get the wrong answer when you're doing calculations. If you say, like here's a streamline, you could say here's 1 and here's 2, or you could interchange it and you'd get the same number. You could say here's location 2 and here's location 1, and even if the flow's going this way, in both cases, you'd get the same answer because the left-hand side of the equation is the same as the right-hand side of the equation. But now look at the energy equation. The left-hand side has different things than the right-hand side. H sub P is on the left, H sub T and the head loss is on the right. So because there's different stuff on the left and the right, that means that you have to be more careful with what you assume for the upstream and the downstream. So 1 refers to the location that's upstream, 2 is downstream, so in the direction of flow. So if we're applying the energy equation, then we always need to ensure that we understand what direction the flow is going. So here, as depicted on the whiteboard, the flow is from the left towards the right. So then that means 1 is upstream, 2 is downstream. So does everybody understand that? Any questions about the flow direction assumption that we build into that? All right, so we have already talked about V bar is the average velocity, and the way that you find the average velocity, V bar, is Q divided by A. So it's the overall flow rate that's being carried by the section divided by the section's area. H sub P refers to the head that's supplied by a pump. And each one of these terms will have units of length. So Z has units of length, meaning either feet or meters. Pressure divided by gamma will have units of length. And so does the head supplied by a pump. And so what we're doing is we're quantifying how much energy has been added to the system in the in between 1 and 2. So let me be very clear that if the system has a pump, but it isn't between your 2 points, then it wouldn't be included in the energy equation. So let's say, here's a pipe. Let's not do it that way. Okay, here's a pipe, and here's a pump. And let's say I'm applying the energy equation between these 2 points. Here's 1, and here's 2. And there's like a house up here. Here's a tank. That's a water tank. So if this is 1 and this is 2, then that pump would not be included in the energy equation. But if the pump is between 1 and 2, then that is when you would include the energy that's being added by the pump in terms of head, then it would go into the energy equation. So the way that pumps work is they add pressure. That's the immediate effect that they have on how energy is added. Is by adding pressure, they'll enable the flow to go more quickly than if the pump wasn't there. But the pump itself doesn't just add velocity, it's adding pressure. And then as a result of the extra pressure, then the velocity is flowing more quickly. We'll talk more about pumps, but H sub P is the pump head. Now on the right-hand side of the equation is the head that would be given up to a turbine. So if you're trying to extract energy, like in hydropower, then the turbine term is on the right-hand side. And the same thing is true that if there's a turbine, but it's not between location 1 and location 2, then it wouldn't be included in the equation. It's only when it's between the 2 points that you're interested in that it would be included. And then head loss, H sub L, is the net effect of friction losses and local losses. So friction losses are due to pipes, and local losses are due to bends in the pipe, fittings and transitions, any kind of localized fitting that introduces turbulence to the flow. It's on the right-hand side because when the water is going from 1 towards 2, the energy is decreasing. What we're saying is that the amount of energy at 1, plus energy added by pump equals energy at 2 plus energy loss due to, like, you'd be losing energy from extraction at a turbine, pipe friction, and local losses. Each of those are ways that energy is lost. And so you can just think about, there's going to be less energy at location 2. There's going to be less energy downstream unless there's been energy that was added by the pump. So any questions so far? Now, the kinetic energy correction factor. Let's talk a little bit more about that. You may remember that when flow conditions are laminar, that there's a bullet-shaped velocity profile. That's just the pipe velocity at the edge. The water velocity at the edge of the pipe is 0 because of the no-slip condition, which means those water molecules that are in direct contact with the steel the pipe is made out of, or the concrete, whatever the material is, there's some water molecules that are directly touching it. Those molecules go the same speed as the pipe, which is to say stationary. And you get a little bit further from the pipe, and then there are some molecules that are able to move at some positive velocity. But the molecules that are in direct contact with the stationary pipe material, because of viscosity, because of friction of the pipe, those molecules can't slip over the surface. And so this velocity profile is related to the shear stress that is applied by the material to the fluid, and also it's a function of the internal resistance of the fluid, which is to say the viscosity. So when conditions are laminar, the water's moving so slowly that the layers don't interact with one another in a turbulent way. Like if there was some sort of a molecule that has a little disturbance, it doesn't start a chain reaction of lots of chaotic omnidirectional flow, but all of the molecules are just essentially going sideways, and if there's some disturbance, it kind of just comes back into a nice equilibrium. Now, if you have a bullet-shaped laminar velocity profile like this, then the maximum velocity is twice the average velocity. Now remember, in the energy equation, what we're using is the average velocity. And so if you just use the average velocity as a representation of how much kinetic energy is actually in the fluid, then you'd be under-representing how much energy is actually there. Because here in the center of the pipe, there's a lot more kinetic energy than is actually represented by just applying the average. So the kinetic energy correction factor is determined by looking at the ratio of the velocity at any particular point to the average velocity and integrating over the entire cross-sectional area. So for a circle, what that means is that when you have laminar flow conditions, you'd need to add a kinetic energy correction factor of 2 in order to have it accurately representing how much kinetic energy is in the fluid if you're going to use the average velocity as your velocity term. But if it's turbulent flow conditions, you don't have that bullet-shaped velocity profile where at the center of the pipe the velocity is so much higher than the average. When conditions are turbulent, the average velocity and the velocity at the center line of the pipe are pretty close together. And so the kinetic energy correction factor doesn't need to be as high because the average velocity doesn't so drastically underrepresent the amount of kinetic energy that's in the fluid. So typically we'd use a kinetic energy correction factor of 1.05, and 1.05 is close enough to 1 that in a lot of cases we won't even bother keeping track of the kinetic energy correction factor unless we're doing really some high precision calculations and we have a lot of accuracy in all of the other measurements. You know, if we're only quantifying the flow rate to within 5 or 10%, then we're usually not so fussy as to include the kinetic energy correction factor. And so in some of the examples we work together, I will include it, but in most of them I won't, because it's a pretty common practice to just ignore the kinetic energy correction factor alpha. Okay, so here's the energy equation. And in this example, what we're using is a formula that characterizes the overall head loss. Remember that head loss has two terms. H sub L includes the pipe friction H sub F and the local losses H naught. So H sub L, head loss, is H sub F plus H naught. So in this example, what we're saying is we've looked at how rough the pipe is. We've looked at whatever fittings and bends and valves there may be. And we're expressing the effect of all of those with this factor 0.04. Because the H sub F formula that we'll use a lot, the Darcy-Weisbach equation, is FLV squared divided by D2G. And the H naught formula that we'll typically use is K times V squared divided by 2G. So here in this example, we're using 0.04 as a representation of pipe friction, the diameter of the pipe, and also the whatever pipe bends may exist. So as we get more sophisticated, I'll actually have you calculate this coefficient but for this example, I'm giving you the coefficient as 0.04. What it basically means is, look at the format of this head loss equation. The longer the pipe is, the higher the head loss will be. So of course that makes sense, that if you have a 50-meter pipe, there would be less head loss than if you have a 100-meter pipe. So length is one of the factors that increases head loss. Another is velocity, and it's velocity squared. So there's a really powerful effect. As the fluid moves progressively faster and faster, the head loss increases by velocity squared. And then, of course, we're dividing by 2g. So the tank on the left is the origin, location 1. Location 2 is the destination, where the flow is going towards. And what we know is the water surface elevation at both of those locations. So WSE just means water surface elevation. So what that tells us is that there's a free surface of water in the tank on the left. So let me just sketch this from a side view. Got two tanks connected by a pipe. Here at 1, we know Z1 equals 200 meters, right? Units meters, yep. Z2 equals 190 meters. And what you need to find out is, what is the flow rate Q? Now, we're going to be applying the energy equation at these two locations. And so, energy equation is P1 divided by gamma plus Z1 plus V1 squared divided by 2G plus the pump head term is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus the turbine term. There's no turbine here, but let's H sub T and H sub L. Okay, so 1 is at the water surface on the left, 2 is at the water surface on the right. So what do we know about the pressure of the liquid at location 1?
Is the tank open?
The tank is open to the atmosphere, yes.
0.
That's right. So it's atmospheric, which we're going to just say 0, gauge pressure. So the P1 term cancels out. The same is true of the P2 term, cancels out. We don't see anything mentioned about a pump, so we can cancel out the pump term and the turbine term as well. There's no description of a turbine. Now, what's the water velocity at 1? Let's assume that these tanks are relatively large in size, and maybe the liquid level is going down very slowly. But what has been our approach in the past when we were at the top of a tank and needing to make a substitution into the velocity head?
0.
We just say 0. Yeah, the velocities may be going down, but it's going down so slowly that it's going to be negligible. Like, even if it was 1 centimeter per second, that's going to make our velocity head term so small relative to the other elevations that it can be reasonably and effectively ignored. So I'm going to cancel out the V1 term. Now wait a minute, I just canceled out the velocity term. Does that mean that there's no water going through the pipe? The pipe does have flow, because it says in the problem statement, water is flowing. So how does water flow through the pipe if I just canceled out the V term?
Because there's a difference in the elevation head.
Okay, that's why there's a flow. You're right, because there's a difference in elevation head. That's why there's flow. But I just said that there's no velocity at 1.
There's no velocity because the area of the tank as a whole is much larger than the diameter, the consequential.
The diameter of the pipe.
Cross-sectional area of the pipe.
So V1 is saying the velocity here at 1. The velocity that goes into this equation, that means velocity in the pipe, not the velocity at the surface of the tank. That V is in the velocity of the pipe. So we've canceled out the pressure head term. So what we're left with is Z1 is equal to Z2. By the way, we're also going to cancel out the V2 term. So Z1 equals Z2 plus HL. That's what's left over. So HL, we have a formula for that. Should we cancel out this V? No, because that's talking about the velocity in the pipe. There is velocity in the pipe, even though we've neglected whatever velocity may exist at the surface of the tank.
I have a quick question. Did you choose not to write the alpha terms because we're assuming turbulent flow and estimating it as 1?
Yes.
Okay.
Yeah, we're just going to,
Okay.
in this example, we'll just jump straight into this kind of sloppy habit of ignoring alpha. All right, so I'm going to pause for a second and have you tell me what's the flow rate. We want to know the flow rate in terms of cubic meters per second. I want to see if you can connect the dots here and identify what's going to be the flow rate through this pipe. All right, so if we take a look at things, we've got this tank on the left, and because of the elevation difference, water will flow through the pipe to the one on the right. We want to know at this particular instant, when the tank elevations are as shown, what's the flow rate? And of course, what we know is that the driving force is that elevation difference, and as the water goes from the tank on the left to the tank on the right, the water levels are going to become more nearly equal, and as the elevation difference decreases, then the flow rate will go down as well. So it's just this particular instant in time that the flow rate will be as we calculate. So you can see the assumptions I've made here about the velocities and pressure at the surface of the tank, and so how that substitutes into each of the terms of the energy equation. And it's a 10-meter elevation difference that's driving the flow. So we need to solve for V squared. And then from that get V. So 4.95 meters per second is how quickly the water will be flowing through this pipe. It's a pretty healthy clip. And with that flow velocity, the flow rate would be 0.476 cubic meters per second. On the exam, as I've been grading some of the papers, what I've noticed is that some of the solutions have a lack of linearity. Now, what I mean is, I think it's reasonable to assume that the early part of the solution is towards the top of the page, and the later part of the solution is at the bottom of the page. You know, like when we read, if you're reading a story, the words that are above are the words that you should read before the words that are below. And I think, like, when you're doing engineering calculations, some of the same approach should be followed. And so just my suggestion is, I know when you're pressed for time, sometimes things get a little bit disorganized, and that's totally reasonable. But when I was grading some exams, you know, like one calculation would be in one corner of the page, and then in a completely opposite location would be the next step, and in between would be some calculations that came after those. So it was kind of like moving all over the place trying to follow. But if you move from left to right and top to bottom, then other people will be able to follow your work a little bit more easily. And you know, when you're working professionally, your calculations aren't really for you, they're for the other people that you're collaborating with, who are trying to understand like why a pipe needs to be a certain size, or maybe you're even communicating to your own self some months or years later, and you're trying to figure out, you know, like what was the basis for a certain decision you made. And so it's really important to be able to like clearly communicate your calculations. Like what you typed into the calculator has no significance and meaning after, you know, the time you press clear. All that vanishes. And the only thing that persists is what you wrote down on the paper. And so that's why I encourage you to like include the units when you're doing calculations, is because having that as a habit makes it more clear what the numbers actually represent. Than if you're just having the numbers with no units, then it's sometimes not as clear that you're talking about a pressure in this location and a velocity in another. So I don't deduct points for sloppy solutions, but I've sure been tempted. And I think it's really important to develop that habit of professional communication. So I'll hop off my soapbox for a second and get back to fluid mechanics. Any questions about this example? All right. Now, what would happen if the water level on the left is raised? How would that affect the flow rate? If Z1 increased but Z2 stayed the same.
It would increase the flow
It would increase the flow
rate.
rate, right. So always think in terms of what's the driving force that's causing the water to go from one spot to another. Here, it's that there's greater elevation at one, and so more elevation will increase that driving force and boost the flow. All right, so let's consider a similar example. Now here, we have water going from two tanks, but we don't know the elevation of the water in the tank. That information isn't available. We have a pressure difference between the two spots, and this is a horizontal pipe. That may not be immediately obvious just from the diagram, but so the pipe is horizontal, which means that these two locations, the elevation is the same. We're working in traditional units here, so we know that the length between these 2 points is 145 feet, and the pressure difference that's measured is 25 psi. PSI, what does that stand for? Pounds per square inch. What a silly unit system traditional units are, because there's 12 inches in a foot. So if we talk about 12 inches by 12 inches, there's 144 inches squared. 144 inches squared in 1 foot squared. Okay, so just keeping that in the back of our mind, we want to find out what's the head loss between these 2 points if the pressure difference between them is 25 psi. So the pressure difference isn't caused by a change in velocity. Think about what can cause a pressure difference. It could be the Bernoulli effect, but here it's not that because the pipe diameter is the same. So the pressure difference isn't changing because the velocity is different at 1 and 2. It's not because of the elevation difference. The pressure difference occurs only because of pipe friction. So it's this pressure difference is directly related to the pipe friction that occurs. And so what you can say is that the pressure difference is P1 minus P2 divided by gamma is equal to the head loss. You know, here in the energy equation, if we compare location 1, so here's tank 1 on the left and tank 2 on the right, but the 2 locations that we could put into the energy equation is here is 1, where we plug in the upstream section of the differential pressure gauge, and here's location 2, where we would plug in the downstream tube of the differential pressure gauge. So between these 2 points, think about what terms are dropping out of the energy equation. The velocity at 1 equals the velocity at 2. So let me just write some of this out on the whiteboard. Oh, I just erased that conversion. I'll leave the numbers. So V1 equals V2. It's not that they're 0, because they're not. You know, if 1 and 2 are in the pipe, there is a velocity there, but since the velocities are the same, that means we can cancel out the velocity term from the energy equation. There's no pump, there's no turbine, there is loss, and we have an equation for that, and Z1 equals Z2. Okay, so with all of that said, calculate the head loss with the pressure difference that's measured, and then use that to solve for the flow velocity with this equation that describes the head loss. All right, so we start off with the energy equation, and how to solve for HL is by substituting in all of the information we have at location 1 and location 2 into the energy equation. So here's a little sketch that summarizes what we're looking at. Okay, so it's a horizontal pipe with taps 145 feet apart where we're measuring a pressure drop of 25 psi. That 25 psi is 3,600 pounds per square foot. And we need to have it in terms of per square foot because the unit weight of water, 62.4 pounds per cubic foot. And we want to know the head loss in terms of feet. So to be dimensionally consistent is why we had to convert from psi into pounds per square foot. Okay, so here's the energy equation, and you can see which terms I've canceled out. At location 1, which is where we've got the upstream tap, and location 2 is the downstream tap. The elevation is the same, so Z1 equals Z2, so that doesn't need to be in the energy equation. V1 equals V2 because the pipe diameter is the same. That means that the velocity through the pipe will be the same at both locations. There's no pump, no turbine, so all that's left is the head loss term on the right and then the change in pressure on the left divided by gamma. So if, earlier I'd written this on the board and you may have wondered where that came from. That just came from rearranging the energy equation and canceling out the terms that don't apply. So 3,600 pounds per square foot divided by 62.4 pounds per cubic foot. So the head loss should be 57.7 feet. That's just converting the pressure change into a head difference. Any questions so far? Okay, now the second part of the question asks, what is the velocity? So we've just calculated that H sub L is 57.7, so that's this, H sub L. So we know the length is 145, we know G is 32.2 feet per second squared, and so the only unknown will be the V term. So we're setting 57.7 equal to, I may not have it on this slide. I've written it in my notes. Let me do it on the whiteboard here. Okay, so our formula for head loss is H sub L is equal to 0.025 length times velocity squared divided by 2g. And I can rearrange that algebraically, like if I'm solving for V, V will be 2 times g times head loss divided by 0.025 times the length, and then all of that is to the 1/2 power. Okay, so then the substitutions themselves, 2 times 32.2 feet per second squared, and this is, just why I think it's a good idea to write the units and not just the number, is if you wrote 9.81 meters per second squared, then instantly you'd recognize, oh, all the rest of the units are feet for length. And so seeing the meters in the midst of the rest of the context having units of feet, you'd avoid the mistake. But if you just write numbers, it's not as obvious. So 32.2 feet per second squared times the head loss, which we just calculated was 57.7 feet. Okay, now divided by 0.025 times the length of 145 feet. Okay, and all of that is to the 1/2 power. What we're looking for is the velocity should be 31.96 feet per second as the flow through the pipe. 31.96. Any questions about this example before we move on to one last question? All right. Now, part of the beauty of the energy equation is that we can begin to take into account the amount of energy that's consumed per unit of time. And so the flow work that's exerted is the pressure forces that are on the outside of a control volume are driving that system as it flows through a conduit. So remember that the Reynolds transport theorem was the idea that we would just define a certain location in space and keep track of the flow in and the flow out through control surfaces, and then consider whether there's any accumulation inside of the control volume that's enclosed by the control surfaces. And so here, what this diagram is just showing is that when water moves from one location at time t to a different location at time t plus delta t, so you can see this is shifted towards the right, what caused the water to move was that work was applied through the pressure forces upstream versus downstream. And so there's more pressure upstream than there is downstream, and the force that's acting on the fluid would be the pressure multiplied by the area. And so if you look at the difference in forces, because the forces on the left push to the right, and the forces that are on the right of the control volume resist that, and so they're pointing the other direction, and the forces on the left are larger, so the net force is acting towards the right, and over some distance, then there's going to be a work involved in that force times a length. And when we want to know the rate of work that's being accomplished, we then consider the velocity. So the velocity term has units of time. And so the fluid pressure multiplied by the area, remember, gives us the force. And then the velocity is some distance, the delta L, per time. So this W dot, the rate of work that's being performed by the system as it's moving through the fluid, is just the difference in the pressures upstream and downstream multiplied by the velocity. So the units of work we're going to talk about as we consider the difference between shaft work, that is the work that's being done by a pump or onto a turbine. In those two new terms in the energy equation, the watts that are being consumed by an electrical motor that's connected to a pump, for example, is what's adding extra head into the system. The reverse of that is that if you have a turbine, that the fluid is spinning the vanes on the turbine, and then that is connected to a generator that's then producing electricity, is also going to have units of watts. So sometimes the words energy, work, and power are used interchangeably, but they have slightly different meanings and contexts. And so energy is usually measured in joules, or here in the energy equation, each of these terms has units of meters, but there's no time component in this representation of the energy equation. So joules are further broken down into a Newton meter. So it's a force of 1 Newton applied over a distance of a meter. That's the definition of a joule. And I guess if we're saying that work and energy have the same units, energy is units of joules and work is also joules, you'd think that maybe those two words can be used interchangeably, but I think the way that our text puts it is that energy is used to perform work. And so energy is the before and work is the after. Or work can be performed in order to store energy. And so like the work that's being done by a fluid that's turning a turbine, that's generating energy. And so the two can be trading back and forth, but maybe the energy is that potential to perform work, and the work is the actual activity itself. Now, power is a little bit different because there's a time dependency there, and so it's how much work or energy is being either consumed or done per unit time. So joules per second. So the power equation is really important. This formula is really important. It's the flow rate of the fluid multiplied by the unit weight of the fluid and then multiplied by the pump head. Now this is the formula that would tell you the amount of power that's required in order to use a pump to add a certain amount of pump head at a given flow rate, and the fluid properties, we would dictate the gamma that we used. The same equation exists also, you could substitute in H sub T. The same kind of equation describes the amount of power that is generated by a turbine. But when we account for efficiency, there's losses, then that's when the turbine power equation and the pump power equation are a little bit different. Of course, in theory, there's a perfect exchange between the electricity that goes into a motor and the power that is added. But the reality is that when you add electricity to a motor, the motor heats up, and the majority of the losses are due to heat. But there's other things as well, like vibration and so on. So when we actually do apply the power equation, we'll generally describe an efficiency factor that either increases the amount of energy that's required to pump fluid or decreases the amount of energy we can extract when it's a turbine. All right, so for our last example today, let's consider another two-tank situation, and we have a sloped pipe. And what we know is it's a 3% slope, and we're measuring the pressure difference at two locations, but this time the pipe isn't horizontal. And so we can't say Z1 equals Z2. And more significantly, the pressure difference that's measured, there's two different simultaneous effects that's occurring. There's the pressure difference that is due to the pipe friction, and there's also some pressure difference that occurs because of the elevation difference. So this is similar to the previous example that we worked. It's just that this time Z1 and Z2 aren't equal. You're going to use the slope and the distance that these two are far apart to define what's the Z1 and the Z2. Okay, so let me pause for a second. Calculate head loss. Solve for H sub L and consider each of the other terms here in the energy equation. Here it is. All right. So the 3% slope means that if we assume that the elevation at 2 is 0, then that would mean Z1 is 16.35. And we don't have to assume it's 0. We could have said, let the elevation at location 2 be 100 meters. And then simply Z1 would be 16.35 meters above that, whatever we had assumed. And we can safely assume that the pipe diameter is constant because it looks like it is, and we don't have any data to the contrary. So that's the only assumption we have, is that whatever the pipe diameter is, it's the same at 1 and 2, so that means that the velocity head terms are going to cancel out. And there's no pump and no turbine, so the energy equation simplifies so that the head loss is on one side of the equation. On the other side of the equation is the difference in pressures divided by gamma plus the elevation difference. Okay, so how much energy is lost? It's going to be the pressure difference divided by gamma plus the elevation difference, so 25.12. So this measured pressure difference would have been even bigger if it wasn't for the elevation difference. Like if it was a horizontal pipe and water was flowing at the same rate, the pressure difference would have been even greater. Any questions about these calculations? Well, I hope everybody has a really nice Thanksgiving. You've got plenty of time for the assignment, so just forget about this class, right? Don't even spend a moment thinking about the homework. Just leave that to a week from after next. And I'll get the scores posted for the exam on Blackboard. If you like to stop by and pick up your test, you can, but I won't be able to go over the exams with you until Tuesday of next week after next. So, take care.